Hello again. I've had a request to talk about how to calculate stress on an inclined plane. That sounds like a pretty good idea. So here you go. Stress on an inclined plane, by the way, is the basis of Moore's circle. So if you want to figure out where Moore's circle comes from, this is a pretty good place to start. Now, the big idea here is that stress is directional. So let me get you an example here. My very, very simple example. This is basically like a ruler or a big popsicle stick. But let's imagine this is a piece of material that's under tension. Now this will work for either tension or compression. But for right now, let's assume tension. And if I grab this and I pull, okay, it's easy to imagine that along a plane right there, there's a normal stress. Well, the stress I measure depends on where I happen to look. So let's say I put a little strain sensor. Let's say I've got a magical stress sensor. Now, as far as I know, there is no such thing as a stress sensor, but let's just say I've got one. And it looks this direction. It's going to see a certain number, whatever this is. It's going to be like force divided by the cross-sectional area. Well, what if I put the sensor on that way, okay, and pull? Well, it isn't going to see anything. Now, there may be some strain this way because of Poisson's ratio, but there won't be any stress that way. So that stands to reason if stress is zero that way and some big number that way, it must be other things at other directions, okay? So stress is directional, okay? We tend to measure strain or calculate stress depending on whatever coordinate systems are convenient. So if I take my little ruler here, it makes good sense to put one of the axes going down that way and another one going this way. But there's no reason to think that just because I pick a set of axes that are convenient, the maximum stress will lay on that convenient axis. It could be something else. It's probably something else. So that's why we want to know Moore's circle, and that's why we want to figure out stresses at some angle to a chosen axis. The axis we choose is a lot of times just for calculation, just for mathematical convenience, not necessarily for a good physical reason. All right? So let's imagine I've got a piece of material like this, and this is a little rectangular piece of material, maybe part of a ruler or like that, or a square rod or something like that. And I've got a force acting on both ends. The forces are equal and opposite, so this piece of material is in static equilibrium. That means it's not moving. There's a better marker here. Right, and let's cut a plane through it, right like that, with that being theta. Okay, so that's the cut right there. Right? Let's say I want to know the normal and the shear stresses on that plane. Well, it turns out we can use a little bit of trigonometry and our basic ideas of stress being force over an area, and we can calculate that. So let's see. Let's say that this is H right there. Okay? And actually, let me draw this I'm going to take a stab at drawing a 3D version of this. That doesn't look too bad. Okay, so there's my piece of material with the forces acting on it. So there's that, and there's the vertical. But let's say I cut it right there. Okay, so let's erase some stuff here. Yeah, not too bad, huh? Okay, so that is going to be B. Okay, and that's H. Okay, I use B and H because we normally define area moment of inertia as being, at least for a rectangle, 1/12 BH cubed. Right? That's theta. And this area here, okay, I'm going to call A theta, the cross-sectional area, the area on which a force acts or over which a force acts, but not perpendicular to the axis. You know, the normal area would be BH. This would be BH modified by something. Okay? So A theta is going to be B, which doesn't change, H, which doesn't change, but the modifier, that's actually H over cosine theta, all right? Or A over cosine theta, okay? Because if that's H, and that's a 90-degree angle, and cosine theta is that line there divided by that, or sorry, that line divided by that line, and we get that being true. Okay, now the other thing I want to know is what are the forces acting on that face, that angled face, all right? Well, I've got a force. I know it acts this way, okay? And that's going to be F. I'm going to call that F normal. That's not a very perpendicular, is it? Let's try this again. there. F normal and F shear. Okay, those are just the vector components of this. So if I know what theta is, I'm going to know what those two are. All right, that's going to be F cosine theta. All right, because if theta is 0 degrees, then F normal is going to be F. Well, that makes sense. And if this goes all the way to 90 or tends towards 90, that'll tend towards 0. So that must be right. And Fs is going to be F sine theta, right? For the same reasons. When this is 0 degrees, that's going to be 0. And when this tends towards 90 degrees, that's going to tend towards 1. And that's going to tend towards F. So this is good. So if I want to find the normal stress on this face here, okay, and I'm going to call that sigma theta, which is normal stress on that angled face, I want F normal over A theta. Well, that's going to be F cosine theta divided by A over cosine theta. Okay, so that's just the normal force divided by that angled area there. Well, that looks like F cosine squared theta to me. That's the normal stress on that angled face. Okay, well, if I figured out the normal stress on that angled face, I ought to be able to figure out the shear stress, and that works the same way. Okay, I need the shear stress divided by the area on that angled face. So the shear stress is F sine theta, and the angled face is A over cosine theta, just like we did before. Remember, it's just F over A, just using the definition of shear stress, shear force over an area, shear force over an area, we're good. And what I get then, by the way, that's got an A over it, that's F over A sine theta cosine theta, right? And all we just did was we used the definition of stress, force over area. I broke my force down into vector components, a normal and a shear component, and I used this area now, which is larger because it's cut at an angle, and so that was the original area divided by cosine theta. So this is pretty straightforward now. One last thing I want to tell you. Right there, pretty obvious that's going to be a maximum when theta equals 0, but what about this? What's the maximum there? Now, we already know that stress is directional. It'll change on a part, even on this little simple part, depending on what direction you're looking at. Well, if you notice that, if you look around you, sometimes columns that are nominally under axial force only, either tension or compression, sometimes don't break perpendicular to their axis. That is, if there's, say this was a column here of a building and it failed because of an earthquake or something, a lot of times they won't break that way. They'll actually break at a 45-degree angle. And if you look on the web, you'll see pictures of bridges and buildings and things that have cracked in earthquakes, and an awful lot of the time those cracks are at 45 degrees. So what's so special about 45 degrees? Well, 45 degrees is pi over 4 radians, right? If you plot sine theta, cosine theta, something interesting happens. And because this is very low tech, I did this on paper. I'll eventually do this on a computer, but right now it's easier to do it on paper and just show you this way. All right, look at that. That looks an awful lot like a sine wave. The only difference is it doesn't go from -1 to +1 now. It goes to something different. And this is, by the way, I'll just write it out here. That's this. That's what I just plotted. All right, you can actually see it there. I don't know if you can see it on the screen or not. But right there, where it's a maximum, guess what that is? 0.25. Well, this is theta divided by pi on that axis. So 0.25 means that's pi over 4. That's where the shear stress is a maximum. And if you did Moore's circle, that you'd also find that at 45 degrees shear stress is a maximum. So what that tells me is there's something special about that 45 degrees. So if I see a column that's broken and it doesn't break along this plane, it breaks along that plane, that's that 45 degrees. That's what this is telling me, right? If you break concrete samples in a testing class and you make these cylinders of concrete and smash them, a lot of times those will break on a 45 degree angle. Same thing going on. So by figuring out normal stress and shear stress on a plane, we're at the beginnings of figuring out what's going on with Moore's circle. Now, what I did here was unidirectional. Okay, there was we're not in. The force is only going one direction here, okay? So we're not quite at Moore's circle yet. To get to Moore's circle, you have to do the general case of a stress element with sigma x, sigma y, and tau xy. And we'll do that in another step. But for unidirectional load along the force or stress along a plane, that's how it works. And the maximum is at 45 degrees, or pi over 4 radians. So there you go.